So, welcome back after the lunch break. And it's a great pleasure for me to introduce Serge Haroche. I think he's one of these scientists who inspired many of us, basically all their scientific life, with his examples and with his wonderful science. And it's a very great pleasure for me to introduce him here. Serge is one of the true pioneers who taught us how to look at quantum physics and how to look the quantum in the eye. Long before, everybody was talking about quantum technologies and quantum computing, and long before this came into our everyday language, he and his collaborators in Paris developed astonishing experiments trapping single microwave photons between superconducting mirrors, sending Rydberg atoms through them as probes. And doing so, he showed quite literally how a photon is born, how the photon lives, how the photon interacts, and how it dies. These are dream experiments, Gedanken experiments, made possible, and really to watch quantum mechanics as it works and how it decoheres. His work laid out the foundations of a whole field of physics, which is cavity QED, and he was also awarded the Nobel Prize of Physics in 2012 for his groundbreaking experiments, methods that enable measuring and manipulating individual quantum systems, together with David Wineland, who did similar experiments in ion traps. Serge was not only an eminent scientist, but he was also an amazing builder of institutions and a mentor for many young and not so young scientists. He was the president of the Academy of Sciences in France, and he is an example of, he was very much supportive of the European Research Council, and I think his research is an example of the ERC philosophy: give exceptional people freedom and trust, and they will move the frontiers of knowledge. Serge, welcome to Vienna, and the stage is yours.
So thank you very much for the warm welcome. It's a pleasure for me to be here and to attend to this joint meeting of the Austrian and Swiss physical societies, and to hear about the wonderful physics which is being done in Switzerland and in Austria. We had very beautiful talks this morning, and my talk would be more historical, and I will be less precise about the description of recent experiments. As you all know, we are celebrating the 100th anniversary of quantum physics, and I thought it was a good illustration to reflect about the history of the laser, because the laser is obviously an offspring of quantum physics, and it also has become, since its invention 65 years ago, a powerful enabler of quantum mechanics and of quantum science, allowing us to discover many new things about the way nature behaves at the quantum level. So in this talk, I will try to recall the lineage of discoveries which have led to the birth of the laser, and then to describe some of the breakthroughs it has made possible in basic science, in blue sky research, and also discuss the possibility of further discoveries. And at the end of the talk, I will reflect about some problems that we are facing as scientists today in these very difficult and troubled times. First of all, I would like to recall that the beginning of the lasers, the roots of the lasers, started well before 1925. In fact, you can find them in the old quantum theory, which developed since Planck's paper in 1900 until 1925, and I've just recalled the different steps. Of course, the first steps was the discovery that light is exchanging energy with matter in discrete steps, And that light, which is a wave, of course, which gives rise to interference effect, is also made of particles, which were later called photons. And this was the work of Planck and Einstein, and introduced in physics for the first time Planck action, the Planck constant, which is playing a fundamental role in quantum physics. A few years later, Niels Bohr quantized the atomic electron orbits and introduced for the first time Planck's constant into atomic physics. Then, 3 years later, Einstein, while studying how matter and light get into equilibrium, was able to distinguish between three processes: absorption, spontaneous emission of light, and stimulated emission, a process by which an excited atomic system is amplifying light. Photons impinging on the system give rise to new photons identical to the photons which were already present in the light beam. And this is, of course, an essential process for the discovery of the laser. Then in 1923, 1924, Bose sent to Einstein a paper in which he described a gas of photons using statistics that was different from Boltzmann statistics, which emphasize the fact that the photons are essentially identical particles. And Einstein extended this process to describe the behavior of atoms, which would also follow the same kind of statistics, and discovered the fact that at very low temperature, these atoms, bosons, should condense into a new phase of matter, which was called later Bose-Einstein condensate. They were discovered using lasers, in fact, much later. And so then in 1924, at the time Einstein was doing this kind of discoveries, he became aware of the works that De Broglie, a young student of Langevin, was doing in Paris, and De Broglie extended the wave-particle dualism that Einstein had introduced for light to matter, and said that matter, which is supposed to be classically as made of discrete particles, must also have a wave nature. And I think at that point Einstein found the connection with the Bose-Einstein condensate and the fact that particles, atoms, could behave as wave, explained why there was this kind of indissonability of identical particles. And he was really excited by De Broglie's work, and he wrote back to Einstein, to Langevin, telling him that his student has lifted the veil which was hiding the mysteries of the quantum world. And he was right, because a few months later, the theory of quantum physics came of age with the paper of Schrödinger, of course, which discovered the equation followed by the De Broglie waves, and with Heisenberg work, which developed in parallel matrix mechanics, which are found to be two equivalent ways to explain the world at the microscopic scale. But before getting into modern quantum theory, I want to discuss another breakthrough, this time an experimental one, which was also very important for the discovery of the laser. And this is the discovery of the two-level systems, discovery of the spin by the Stern-Gerlach experiment. I don't know why I don't have it here. Yes. On the left part of this slide, I had a picture of Stern and Gerlach. I don't know how it does not show up. I hope it has nothing to do with some geopolitical reasons. But the important point here is that I show you on this part of the slide the setup that Stern and Gerlach used. In fact, they wanted to measure the magnetic moment of atoms, and for that they sent silver atoms on an atomic beam through the gap of a very powerful electromagnet. The magnet produced a gradient of the magnetic field, and the force exercised on the magnetic moments were just deflecting the magnetic moments, and what they expected to see was a continuous trace, because classically one expects the projection of the magnetic moment in the direction of the gradient should vary continuously. And as we know, they were surprised to see instead that there were two spots, and this was the discovery of the spin. In fact, what they had discovered with this experiment is the electron spin, the magnetism which was carried by the silver atoms. And this setup separates the magnetic moments pointing up and down it shows for the first time spatial quantization and the existence of two-level systems in physics. These are the future qubits. And of course, the laser works on essentially on a two-level system. You have to invert the population and then to look at the amplification of light. And you see on the left part of the slide the kind of trace they observed, two spots which were joined in the edge because the gradient of the magnetic field decreased, and so the two spots were connecting to each other. But this double slit result was very interesting, and Stern and Gerlach understood the importance of this, and they were very enthusiastic about that. They printed this on a postcard that they sent to Niels Bohr in Copenhagen. In fact, on the other side of this postcard, you had the address, and it was just written Niels Bohr, Professor Niels Bohr, Copenhagen, and it was enough to get it there. And they wrote, of course, I don't have to translate German for you, but what they said essentially is that we congratulate you for the confirmation of your theory. And the important point, of course, is that it's not Niels Bohr theory. Niels Bohr had quantized the orbital momentum of the electron in his famous 1913 paper, and here is the proof of the quantization of the intrinsic angular momentum of the electron spin. So it's a kind of confusion between the daily precession of the Earth and the yearly precession around the Sun. Nevertheless, it's true that Bohr was the first to quantize any kind of angular momentum, and so it explains why it was interesting for them to send this postcard to him. And what I want to stress is the fact that, I don't know why, again, it doesn't work. Yeah. I want to stress the fact that this split trace on the glass plate announces the 20th century quantum revolution in technology and the qubit in the 21st century. So I thought it was interesting to show that here. But more blue sky science had to be done, and I have now to recall what Isidore Rabi, which was also mentioned this morning because his name was given to the famous Rabi oscillation that is so important now in quantum physics experiment. Rabi was a postdoc of Stern in Hamburg, and he came back to the United States at the end of the 1920s and imported at Columbia University the technology of atomic and molecular beams. And what he wanted to do is to measure the nuclear magnetic moments, which are 3 orders of magnitude smaller than the spin of the electron. And for that, he built a kind of refined version of the Stern-Gerlach experiment. Now you had 2 gradients of magnetic field in zone A and B. The gradients are in opposite directions, so they channel the particles into an S-shaped trajectory, which is focused on a hot wire. And the hot wire, the molecules of the atom lose electrons and give rise to an electric current, which is proportional to the flux of particles reaching it. The important point in the experiment is what happens between A and B in zone C, where a radio frequency field is applied. This field is applied at a frequency making the spin switch from the up to the down state. And this is this was the first setup which demonstrated magnetic resonance, nuclear magnetic resonance. So when you sweep the radio frequency to be in resonance with the transition between the 2 levels in a given magnetic field, you get the particles go out of focus with the wire, and you get a decrease in the signal. And so what you see is the first resonance that Rabi obtained in 1939. And what I want to stress is that this signal is announcing the nuclear magnetic resonance, the medical resonance imaging, atomic clocks, the GPS, optical pumping, and the laser. And this was very important. And Rabi had a premonition of that. I have found on the internet this copy of an article which was published in the New York Post in December 1939. The journalist had attended a lecture that Rabi had given in a conference of the American Association for the Advancement of Science, and Rabi had said something like that: we are all radio stations. All atoms in humans are found to emit and receive long waves. In fact, I think Rabi had said that the atoms he had in his atomic beam was the same as the one we have in our bodies, and that they should absorb and emit radio waves. And this struck the imagination of the journalist. Of course, to transform this into an MRI machine, you need many more steps. You have to exploit the quantum properties of atomic spins, but not in atomic beams. You cannot detect the atoms in our body on a hot wire. What you need is to have a detection which is non-invasive, and this is what has been done by Bloch and Purcell in 1945. They developed NMR in bulk materials, and this has led later on to the magnetic resonance imaging. Rabi had another premonition. He said, and discussed with his students and postdoc in the 1940s, he said that one could use magnetic resonance to build atomic clocks. In fact, they had discovered in their experiments that alkali atoms like rubidium and cesium have a two-level structure in the ground state. The two levels correspond to the spin, electron and nuclear spin, either parallel or anti-parallel, and between these two levels, you have a transition at a frequency which is of the order of several gigahertz, 9.2 gigahertz for cesium. And Rabi had explained to his students that if you can lock a microwave source to this transition, you would have a frequency standard that could be used to define time with precision. For that, you had to find a way to detect the center of the resonance with precision, and this was done by one of Rabi's students, Norman Ramsey, who developed the method of the double resonance of separated oscillatory fields. Instead of submitting the atom to a single microwave pulse, it's submitted to two pulses separated in time as the atoms move along the atomic beam. This gives rise to a quantum interference effect. Instead of having a Lorentzian shape, you get fringes, and the central fringe can be made very narrow. And if you lock your microwave to the central fringe, you can have a source of microwave which is very, very stable. Before that, all the clocks were detecting oscillation of man-made devices whose frequency was just arbitrary. Here you had for the first time a clock which is based on a device which obeys to quantum laws, and all cesium atoms in the universe have to oscillate at the same frequency. So it gave a big jump into the precision, into the stability, and also into the precision, because the frequency of this clock, 9.2 gigahertz, is orders of magnitude higher than the one we had before with pendulum or quartz clocks. And of course, we know that after many developments, this has led to the GPS system. This kind of atomic clocks embarked in satellite give us signals which allow us to find ourselves at the surface of the Earth with a precision of about 1 meter. So this comes from this kind of experiment. Another pre-laser invention, the fact that you can manipulate atoms with light by optical pumping, and this was the work done by Kastler and Brossel in Paris in the 1950s. What they discovered is the fact that you can change the distribution of population between atomic energy levels by having it interacting with polarized light. And in fact, Kastler was very much influenced by Rabi, by Sommerfeld and Rabi, and in fact what he did in this experiment is an extension of the Stern-Gerlach experiment. Instead of having lasers, atoms manipulated by gradients of static fields, he manipulated atoms with light waves, and of course the principle of the interaction is the same. And in one of the papers that Kastler wrote, he said that this could be used to change the relative populations between states and to get some cooling of matter. But he was very modest, and he said this is a kind of strange effect, and it will not be very important. It's just a kind of footnote in one of his papers. He calls this the effet lumineux photographique, this light cooling effect, which became very important, as we know, in the future. One of Kastler's students, Kastler and Brossel student, Claude Cohen-Tanucci, made the theory of optical pumping, and at the same time did very beautiful experiments, and he discovered the light shifts. He discovered the fact that if a light is not resonant, not exactly resonant, it will not be able to be absorbed by the atoms, but it will shift the energy levels. And these shifts, of course, have become, at that time, they were very, very small, of the order of 1 Hertz, and could be detected only because of the extreme sensitivity of optical pumping methods. But now with lasers, this shift becomes of the order of gigahertz. They can change over a distance of the order of 1 wavelength in the gradient of field, and it gives rise to enormous forces which can be used to trap atoms, to cool them down. And of course, this is the basis of laser cooling methods. Also, these light shifts are also used in cavity QED to count photons in a non-destructive way. So it has also been a very important discovery. So we now come to the time of the discovery, invention of the laser, and we have to come back to Columbia University. You see here a picture showing Charlie Towns with his student Gordon in front of another molecular beam machine, an ammonia beam machine, which was the first system which gave rise to coherent radiation produced by atoms or molecules. In fact, you know that the ammonia molecule has 3 hydrogen atoms on a plane and 1 nitrogen atom out of the plane, and this nitrogen atom can be on one side or the other of the hydrogen plane. It's a 2-level system, and the symmetric and antisymmetric superposition of these states are the AERG eigenstates of the system, and as the nitrogen atom flip-flops across the plane by tunnel effect, it's kind of the Rabi oscillation between one quantum state and the other. And so this was the first system which was used to amplify and to have an oscillator operating in the microwave domain. And the acronym for it's, of course, a MASER, microwave amplification by stimulated emission of radiation. Now, another step had to be taken to get the same system working in the optical domain. At first, Towns thought that it could be achieved by optical pumping methods, and before I came to the Kastner-Brossel lab at the end of the 1950s, Towns spent a few months trying to learn about optical pumping, but optical pumping was not the process which was used for the first laser. It's Theodore Maiman which did it in a ruby rod, and the optical MASER laser was born at that time, and the story starts in 1960. The laser had been invented, and as we know, it has been an extraordinary source of tamed light. So on the next slide, I just summarize the main properties that we all know about. It's a source of intense, directive, monochromatic, and coherent radiation. It has very paradoxical properties. It can be used to heat matter at millions of degrees. It can also be used to cool matter at nano-Kelvin, micro or nano-Kelvin temperatures, and give rise to new phases of matter like Bose-Einstein or Fermi-degenerate quantum gases. This is properties linked to the possibility of exchanging momentum and energy and momentum in a very well-controlled way between matter and radiation. On the other hand, this is an ultra-stable source of light. It can oscillate without skipping a beat over millions of kilometers for propagation, and this gives rise to fantastic sources for spectroscopy, for ranging, for interferometry at long distances, and also by making this light beam interfere with each other, you can produce very ultra-short pulses of light in the attosecond domain, which have revolutionized the kind of physics you can do at a very fast rate. So it's very important, a very important tool for fundamental research in physics, chemistry, and biology. Just to illustrate this point, on this slide, I have summarized the progress which have been made since the invention of the laser in many directions. And what I want to say is that, in fact, more than 10 orders of magnitude of improvement have been reached. 10 orders of magnitude improvement in 60 years means a factor of 10 every 5 years. So think about it. During the time scale of a PhD thesis, the progress in all this direction has been by at least 1 order of magnitude. So let's look at a few domains. The temperature and kinetic energies of atoms. Before the laser, you work at the coldest temperature were of the order of 1 Kelvin in atomic physics, maybe millikelvins in condensed matter physics, but now we can reach nanokelvins and even less with cold atoms. The precision of spectroscopy. Before the laser, the most precise atomic spectroscopy experiment, like, for example, the measurement of the Rydberg constant, gave 8 digits. The measurement of time before atomic clocks and before done with quartz clocks was also at the precision of 1 part in 10 to the 8. 1 millisecond per day was the best quartz clocks. Now we reach 10 minus 19 to 10 minus 20. So it's again more than 10 orders of magnitude. The sensitivity of measurements in an optical pumping cell, the kind that Kastler and Borsell were using, you had billions of atoms. Now we can just observe a single atom, a single photon. Excuse me. There's nothing to do with physics. The speed and time resolution, the shortest light pulses you had before that were in the range of a spark gave pulses of the order of microseconds or nanoseconds. Now you can reach attoseconds, as I said before. The sensitivity to length variations, in the measurement of the definition of the meter before the laser was done by interferometry, Michelson interferometer, measuring the wavelengths of a krypton lamp. It was measured with a precision of 1 part in 10 to the 8. Now, with the LIGO and Virgo gravitational antennas, you make a measurement of relative changes in lenses in 1 part in 10 to the 21 or 10 to the 22. And I will start with this because I think it's a very striking example. I'm sure that you all know the signal which shows the first detection of gravitational waves on Earth. You see the black and red signals come from 2 antennas, one in the north of United States and the other one in the south. It's the 2 LIGO antennas, and I will come back to this later. And this oscillation reveals the collapse of 2 black holes, which the last revolution of 2 black holes rotating around each other, which merge and emit a huge amount of energy, several solar masses released in 1 second, which is an unbelievable amount of energy. And this gave rise to a ripple of space-time, which propagated over billions of years. And the result was this very, very small signal, which, if you look at orders of magnitude, it's less than 10 billionths of an atomic diameter difference between the 2 arms of the interferometer over a distance of 4 kilometers. It's 1 part in 10 to the 21 or 10 to the 22. So it's a real tour de force in precision, and it is due to the fact that we can have so stable lasers, powerful and stable lasers, and of course also a lot of technology to avoid all kinds of vibrations. The mirrors are fantastic achievements just in pure mechanics. What I want to stress is the fact that Einstein physics can in fact be described between 2 Michelson experiments. You had, of course, the first Michelson experiment, which was a negative experiment. It showed no difference in the time for the light to travel between 2 mirrors in 2 orthogonal directions, showing that the velocity of light does not depend on the velocity of the observer through space. And this was explained by the special relativity theory. Negative experiment, in fact, it would have been sensitive to a displacement of fringes of 1/10 of a wavelength. So it was sensitive enough to see no difference at this level. And then the second Michelson experiment, the one I just discussed before, was a positive experiment which showed a difference. But for that, you needed a sensitivity to fringe shift of 1 part in 10 to the 12 of the wavelength. So you see again an 11 order of magnitude improvement over pre-laser physics. A few words about laser cooling. You see here at the intersection of laser beams a bright spot, which is an optical molasses of sodium atoms, which has been observed in the lab of Bill Phillips. And these atoms fluoresce and they are very cold. Temperature is of microkelvin. If you look at the theory, you find that this microkelvin temperature cannot be explained just by exchange of photon momenta. In fact, the predicted temperature was hundreds of microkelvin, and it's a rare example of experiment which does better than what the theory is predicting. And in fact, this is due to the fact that the rubidium atoms have in the ground state this two-level structure. And so there is a combination of light shifts and optical pumping which cools the atom even more. This is called the famous Sisyphus cooling effect, which was explained by Claude Cohen-Tanuji and Jean Dalibard. The interference between the laser beams is such that the atoms see a landscape of optical hills and valleys due to spatially varying light shifts. And when they reach the top of a hill, the optical polarization of light is such that the optical pumping brings the atom down into a valley. So the atoms have to keep climbing hills all the time, hence the name Sisyphus effect. And this explains the cooling, a very effective cooling process, which brings the temperature down to microkelvin. If you add to this a process of evaporative cooling, which was developed by Cornell and Wyman, and then by Ketterle at MIT, you get, of course, the Bose-Einstein condensation, which was obtained for the first time 30 years ago. That is 70 years after its prediction by Einstein. And this new form of matter leads to the possibility to do a lot of beautiful interferometric experiments. Especially, you can, for example, make atom lasers, kind of coherent matter waves in which photons are replaced by atoms, and which have basically the same kind of properties as a laser beam. And of course, to the beautiful and very rich physics that we heard about this morning. Another application I want to stress is the atomic optical clocks. Now you can have clocks which are based not on microwave transition, but on optical transitions, and this is in particular the work which is being done by Jen E. in Boulder and also by Katori in Japan. These clocks oscillate at a frequency which are 5 orders of magnitude higher than the microwave clocks, and the precision increased by this order of magnitude. The uncertainty is now of the order 10⁻⁹, 1/20th of a second over the age of the universe. So these clocks are 100,000 times more precise than the GPS clocks. They are sensitive to general relativity space-time curvature over 1 millimeter altitude difference. It means that at the top and the bottom of the clock, the time does not go at the same rate. And so it's a really fantastic thing. And since I'm talking about the laser, I want to stress that you need 4 different kinds of lasers to do that. You have one laser system to cool the strontium atoms, another laser system used to trap these atoms into an optical lattice to keep them free of motion, so they don't have any Doppler effect. You need a laser, very stable laser, to excite the strontium transition and to interrogate it. And you need a frequency comb laser to transfer this frequency stability to the microwave domain. And so this is the kind of precision we have now. And there is a hope to go to even more precise nuclear clocks in the future if you can develop laser combs in the vacuum ultraviolet and use nuclear transitions, which now start to be investigated with a very high precision. I want also to, of course, to mention the fact that you can non-destructively manipulate single atom and molecule with lasers. And again, I stress the fact that instead of looking at ensembles, huge ensembles of atoms like in the optical pumping cells, now you can interrogate individually, for example, ions in this kind of traps that have been developed by Dave Wineland in Boulder and by Rainer Blatt and his group in Innsbruck. And you can use each of these atoms as a quantum bit which can store information. You can have these bits talking to each other through the coupling to common vibration modes, and you can do elementary demonstration of quantum computing with the system. I don't want to get into these details, but this is a very active field of research now. In this experiment, you use light to interrogate matter. You can do the opposite, and this is the kind of experiment that we are doing in Paris. You can trap photons in a superconducting cavity, and send atoms one by one through the cavity. The kind of atoms that we use are Rydberg atoms because they have to be very sensitive to microwave fields. And we use the Ramsey technique for that. You can, you have before and after the cavity, you sandwich your high-Q cavity with two zones in which you apply microwave pulses. So you get Ramsey interference fringes. These fringes are very sensitive to the light intensity at the photon level. So you see in red and in blue, here are the fringes that you get when you have 0 or 1 photon in the cavity. And you see that you can change the phase of the fringes by pi, which means that if you stay at the top of a fringe with 0 photon, you are at the bottom of the fringe with 1 photon, which means that it's just one atom going through the cavity can tell you whether you have 0 or 1 photon inside. And we use that to detect single photons, and this signal shows, for example, the birth, the life, and the death of a photon in the cavity. And you see that hundreds of atoms witness the fact that you have 1 photon in the cavity, which is completely different from the ordinary photo detection effect, in which the first atom would kill the photon. So this is a kind of experiment that we have developed to show that you can use this system to build quantum gates in which the photon controls the atom, so inversely, or you can store information in the field. And this is, of course, the basis of cavity QED experiments that we did in Paris and which have been generalized to circuit QED, in which Rydberg atoms are replaced by artificial atoms made of Josephson junctions. And so it's a very active field of quantum information science today. The sensitivity of Rydberg atoms can also be used in a different way. Instead of looking at the interaction of Rydberg atom with microwaves, you can look at the interaction between Rydberg atoms. And this is a field which has been very active during the last 25 years since the proposal to use this to build quantum simulators. You see on the left that you can trap two atoms in in a tweezer trap made of focused light beam at a very well-defined distance of a few micrometers. If you try to, you can excite one of these atoms into a Rydberg state, but once you have done that, you cannot excite the second one with the same laser, just because the atoms interact so strongly with each other that the first atom put the other atom out of resonance with the laser. So you cannot do that. And if you try to excite the two atoms simultaneously with a very wide laser beam, in fact, you can only send excite only one excitation to the system. And what you prepare, in fact, is an entangled state in which the excitation is equally shared between the two atoms. So it's at the same time you excite the first atom, the second one remaining in the ground state, or the opposite. And this is an entangled state, which means that you can use this kind of interaction to entangle atoms and to build quantum gates, because the basic fact to make a gate is to be able to get an entanglement with this kind of nonlinear process. I described this, what happens with two atoms. Of course, now this is generalized to a tweezer array of atoms in which you can make in a plane hundreds of atoms, locate them in the ground state and try to excite them into Rydberg state. And the Rydberg blockade effect gives rise to a kind of very complex entanglement, and you can use that to simulate what happens in ferromagnetic or antiferromagnetic materials and study other many-body condensed matter systems. And this is a very active field of physics, and it's also research which is very closely linked to the research done on quantum computers. The last example that I want to give is experiments which have not yet given positive result, but which is very promising, which is a search for new physics with ultra-precise laser spectroscopy, looking for the electron-electric dipole moment. According to the standard theory, the question is the electron exactly spherical or not? According to the standard quantum model, the electron is just a spherical system which has no electric dipole moment. An electric dipole moment would require a violation of time reversal symmetry, and at the level of the standard model, this violation is very small, so the electric dipole moment should be smaller than 10 - 36 electron centimeter, according to the standard model. But you have some models outside the standard model which predict larger supersymmetric time reversal violations, which would give a dipole moment of the order of 10⁻31 to 10⁻32 electron centimeter. And this is something which is experiments are aiming at. These experiments are very difficult. You have to look at the precession of the electron spin in a magnetic field, and then you add an electric field, either parallel or anti-parallel to the electric field, and you look at a very small variation of the Larmor precession frequency. Very, very small, because the effect is very small, and you cannot reach these electric fields directly. What you have to do is to put your electron in a molecule having a very heavy nucleus, because then you have a kind of amplification of the external electric field, giving you a huge internal electric field in the molecule. And the way you do it is you do Ramsey spectroscopy, and you try to look at a very small displacement of fringes. There are at least 3 groups in the world which are competing in this field at Harvard, Imperial College, and in Boulder. And for the times, at the present time, the precision of the present experiment is 4⁻33 electron centimeter, about 1 order of magnitude away from what is needed if there is some new physics. I want to stress how small this quantity is. If you assume that the electron is a kind of non-spherical, a kind of football, American football distribution, the difference between the radii in 2 directions is only 1 part in 10 to the 17. 1 part in 10 to the 17, if you blow up the electron to the size of the Earth, is the size of an atom, 1 angstrom. So you want to see a difference of about 1 angstrom on the size of the Earth. But if you see this difference, then it means that this could be an evidence of new particles. These new particles could maybe have a connection with dark matter, so it would have very important implication for quantum physics and cosmology. And this is, of course, curiosity-driven physics. There is no direct application for the time being. But I want to use this as a closing argument to tell you something about curiosity-driven research and about the passion for precision in blue sky science. The question I just raised, is the electron perfectly spherical, is connected, is similar to this kind of question which was asked in the 18th century. Is the Earth exactly spherical or not? And this question was raised at the Science Academy in Paris by Maupertuis, who was a mathematician and a physicist. And of course, there were 2 models. In fact, Cassini was the royal astronomer, thought that the Earth was prolate like a lemon. And Newton and Huygens said, no, the Earth should be oblate because it's rotating, and the rotation should expel matter at the equator and give him an oblate shape. So this was a question, it was an open question. And so the French Academy sent 2 expeditions. Maupertuis was sent to the polar circle, and La Condamine to the equatorial region in South America. And they made the measurement of the distance between 2 points separated 1 degree of latitude over a meridian. And it should be smaller at the equator than at the pole if the Earth is oblate. And the experiment was done, it took 10 years, more than 10 years for the La Condamine expedition, 2 years for Maupertuis, and they found that the result was positive and was vindicating Huygens and Newton. I want to stress that the effect is much larger than what we are looking for now. It's 1 part in 10 to the 3 part in 10 to the 3. I also want to stress that Maupertuis has a deeper connection to what I am talking to you today, because it is also the phase of the least action principle. And I told you the fundamental unit of action is Planck's constant. So Maupertuis had something to say also about the physics we are talking to you today. And I want also to say the scientific method has not changed. Doing research has always taken time and money. And the time it takes to measure the electric dipole moment of the electron is of the same order of magnitude as the time it took for this expedition, tens of years, and doing experiments again and again. At that time, it was more dangerous. Some people died in both cases, which is fortunately not the case now. I want also to tell you that already at that time, you needed to justify what you are doing because of its usefulness. And what Maupertuis wrote in his the presentation of his observation was the following. The Academy was thus divided. Its own lights had made it uncertain when the king wanted to decide this great question, which was not one of those vain speculations with which the idleness and useless subtlety of philosophers sometimes occupies themselves. So this is what Trump thinks about science, basically, but which must have real influences on astronomy and navigation. So I am not sure he believed in that, but at least he had to say that to get the money to go to Lapland. And I want also to stress the similarity between the research at that time and the research now. Everything is based on curiosity. At the beginning, you have to test theory by observation. You cannot just decide Newton is right, that's obvious, we don't need to do the experiment. You have to do the experiment. You need to justify utility. You need to have time, to have the trust of the people who give you the money, and you need money. You have to use the latest optical technologies. Now you have very precise lasers. At that time, Maupertuis used sextants, which were developed to measure the aberration of stars, which, by the way, gave the first precise measurement of the velocity of light in the 17th century. So he used the best instrument of the time, and it required large teams and international collaborations. Maupertuis traveled with Celsius, a Swedish Celsius scientist, and he collaborated with Bradley, which was a British astronomer in London. You also need to make systematic error evaluation, and it's amazing to look at the Maupertuis paper in which he describes in detail how they avoid systematic errors and how they measure the precision of the experiment. Now, 3 centuries later, lasers make possible geodesical surveys of Earth, which confirm Maupertuis' result, of course, with a much higher precision. The Earth is not really an oblate ball, but it has a lot of irregularities which are due to the inhomogeneity in the distribution of masses. So in conclusion, I want to say that I think this illustrates the importance of lasers in basic science. I want also to stress the fact that lasers have inherited many tools which were invented in optics and atomic physics in the pre-laser era. It used Ramsey spectroscopy, it used Stern-Gerlach kind of focusing forces, it used optical pumping, a lot of techniques which were made before the laser, and this illustrates the fact that each generation of scientists is building up on the knowledge which has been acquired by the previous one. So it's very important to take notice of what has been done before. The history of science, I think, is a very important way to do science. The passion for precision is at the heart of the scientific method, and we can expect other breakthroughs in which laser will again be essential. I give on the left some references. I wrote a review paper on the laser, which basically develops what I have been telling you today. And if you want to learn more about the history, I have also written a book about the science of light, in which I describe in detail, for example, this Maupertuis and La Condamine expeditions. And this also illustrates the deep connection between basic and applied research, and I think this will be the topic of our next panel discussion. Now, if I have 1 or 2 more minutes, I want to stress some important point now. We live in a time when science is dangerously challenged, and for that I show you here an article which was published in the New York Times a few weeks ago, saying that scientific discoveries, research breakthrough are often sagas of passion, curiosity, and sacrifice. And they go on saying, if Trump's proposed budget cuts for 2026 are enacted, many such journeys may never get started. And the article gives a very precise example. In a budget released on Friday, the administration proposed cutting the budget for the LIGO gravity wave detectors by half. Enough money to operate only one of the antennas. And so it's no ability to triangulate incoming gravitational wave signals. So you see what happens when you when you have an administration which does not believe in science, which hates science, in fact, and which hates education, and when they put in charge of administration and government crackpots. That's the only way you can define the people who are at the head of this administration. And so I think it's a very dangerous thing. In fact, I think that we should defend the scientific truth against the rise of alternative facts. We should distinguish science from conspiracy theories. But this is something obvious. I think also we should discuss research without hype and without overselling. And you should not make exaggerated promises. I think science is marvelous enough not to require to do science fiction at the same time that you do science. And we have to remind ourselves and the public that the principal motivation of science is curiosity. I think these issues are permanent issues. They were already very present to the mind of scientists 80 years ago, and I show you here a sentence which was written by Abraham Flexner, who was the first president of Princeton Center for Advanced Study. He wrote this sentence that I let you to read for yourself, and this was the first sentence in a book that he called The Usefulness of Useless Knowledge, in which he developed this idea that science is done for curiosity and that the application comes after that. And he described a situation in which scientists are doing their research, they detach themselves wholly or partly from the angry current of daily life, and they devote themselves to the cultivation of beauty, the extension of knowledge, the cure of disease, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. And this was written in 1939. So I think we have to reflect on that, and we have to try to do something against that, because we have some things that they did not have that time. We know what happened, and we know what should we do, I think, to make it not happen in the future. So I will stop at that point. Thank you.
So thank you, Serge, for this wonderful talk. Are there maybe a very short, some very urgent questions or comments on him, and then I will give over to Silke for the other things. Do we have some very urgent questions? Yeah. No. Yes.
So I have just one question regarding the electron, the EDM experiment. So why, let's say, the confirmation of an EDM will bring to the discovery of new particle? What is the link?
I am not a specialist of that, but I think superstring theory predicts the existence of particles which would appear in a virtual way. Particle will be part of a vacuum, including the field of these particles, and this would give very small changes to the properties of matter that we know today. A little bit like the lamp shift. Lamp shift is due to the electromagnetic vacuum, which changes slightly the position of the hydrogen level of the atom. And here, these supersymmetric particles would slightly change the electric dipole moment of the electron, so it would be a kind of virtual proof of the existence of these particles. And I think this is the advantage of high precision measurement, because if you want to really create this particle in the lab, you need huge accelerators, and there is a limit to the energies that you can reach with an accelerator, whereas there is no clear limit to the precision that the experiment can achieve, because if you look at the evolution, you have a kind of exponential increase in precision since during the last 6 or 7 decades, and this can, I don't know how long it can go, but we have not reached the limit of that, and so maybe this will give positive results.
Jörg, there was a second.
Do you think that the speed of communication, the speed and the availability of information, which has increased by many orders of magnitude in the last few years or even decades, similar to the laser improvement, is that part of our problem we are in right now, as you described it at the end of your talk?
The speed of communication is basically the speed of light. It's, of course, it's amazing that you can communicate now everywhere in the Earth at the speed of light in optical fibers, which is a little bit smaller than the actual speed of light in vacuum, but still very large. And what is also clear is that quantum physics does not allow you to go faster. The kind of the entanglements, the non-localities that you get does not give you the means to communicate faster than the speed of light. And so there is no contradiction between quantum physics and the special or general theory of relativity, which is, I think, quite astonishing, because Schrödinger's equation is a non-relativistic equation, but still it is compatible with the principle of special relativity. So we still have to understand some mysteries, positive or negative mysteries.
Mm-hmm. Okay, now I invite everyone to stay here because we have a panel discussion on topics that Serge already alluded to, so going from blue sky research to technology in the field of quantum physics. And we have an exquisite panel. And I welcome all panel members to take your seats in front. And Serge, you may start and sit somewhere nicely in the middle.